Okay, I decided that I wanted to do one more video on rotational motion before we finish this up, this kind of overview up on rotational motion, and that's torque with angles. So if we look at this then, we have a long thin rod, and we'll say that it's 10 kilograms and has a length of 4 meters, and by the length I mean that total length. What that says to us though is that there's going to be, here I'll call this R1, and I'll call it negative 2 meters. And then over here we'll have R2, which I'll call positive 2 meters. And really what we're interested in is how much perpendicular force is there. So how much of whatever force we have is actually going perpendicular to the lever arm. And so if I look at this, there's going to be a part of F2 that's perpendicular, and there's also a part of F2 that is parallel, and I really just want that perpendicular part, and that's apparent in the equation when we look at it. So the torque equation is R cross F, and another way of writing that is R F sine of the angle between them. And if we look at this perpendicular component here, I can get that by taking, because if this is my angle in here, okay, so that's my 30-degree angle, theta 2, that, if I take the sine of that angle, I get the y component of the force, the perpendicular component of the force. So it's important that I understand that this is what I'm going to do, and also that I need to use the sine of the angle between the r vector. So here's my r vector. Right, that's my R2, and this was my F2, and it's the angle between that's the relevant angle here. If I don't do this, then I'm missing a lot of the point of the rotational process. We definitely need our force to be tangent to whatever circle this is going to undergo. You can imagine that there's this circle here, and even though it looks more like an egg, and if our forces aren't perpendicular to the circle, then they're not really doing much to twist it. So you need tangent, I should say, tangent to the circle. Those are going to do the most in terms of causing a rotation. Ones that are more in and out of the circle aren't going to really do very much at all. And so this is kind of in between. So it's going to do some twisting, but it's not going to do that much. And I made a point of making these equal forces. So I have two equal forces. They do not, however, cause equal torques, because this one is not exactly tangent to the circle. Now for this problem, what we're trying to find is the angular acceleration. So there's a couple things that we need to do here. First of all, we'll do the sum of torque equals I times alpha. And we have two torques. We have torque from 1 and we have torque from 2, and that's going to equal 1/12 ml squared. I'll actually use a lowercase l. I prefer them. Keeps us from getting confused with angular momentum. So I'm going to use ml squared times alpha times 1/12, and that's going to be T1 plus T2. Now this T1, it's pretty easy because I've got a negative 2, and I'm just going to treat down as the positive direction. Here, so this is the positive direction, that's the negative direction. Makes it easier than throwing in negatives everywhere. But I have a sine of 90 degrees. If I plug this in for T1, I'm just going to get R times F. Okay, so I'm just going to get R1 times F1, because if I plug in the sine of 90 degrees, I'm just going to get 1. So we're not going to even bother. But with this one, I kind of have to. So I have R2 F2 sine of theta 2 equals 1/12 ml squared alpha. And now I can pretty much just solve for alpha. It's a little bit strange. You might be wondering, what about gravity? Well, I was actually thinking that this was a bird's eye view, a top-down view. But even if it wasn't, even if there was a force of gravity here pulling down, that's not going to cause anything in terms of twisting because it's acting exactly at the center of mass. So once again, imagine that you have this circle, and if there's this force downwards from the center of mass, it's radiating out from the circle. It doesn't do anything to cause a twisting. But in any case, this is a top-down view. So I have R1 F1 plus R2 F2 sine theta 2, and I'm going to solve for alpha. So I get alpha equals R1 F1 plus, oops, 1 plus R2 F2 sine theta 2 divided by 1/12 ml squared. And we can clean this up a little bit, and that's what I'm going to do. R1 F1 plus, and I'll just make this 1/2 R2 F2. I make that 1/2 because the sine of 30 degrees is 1/2. And we'll do this whole thing times 12 over ml squared. And so now I can plug stuff in. So we have -2 times 20 plus 1/2 of 2 times 20. So this is my R1 and F1, negative because it's in the opposite direction, so I do just define my axes. So this is the negative direction, that's the positive direction. And 1/2 is of course because of the sine of 30 degrees. And then down here we'll have 10 times 4 squared. And so our alpha, if we look at this top part here, well that's -40, that's +20. So we end up with 12 times -20 divided by 160. And we could do some simplification here if we wanted to, but we don't need to do that much. So we'll just leave it as this quantity, radians per second squared, and it is negative, which is indicating that it's rotating in this direction in this case. So the overall torque is negative. The main points that I want you to get across from this is, well, first of all, this is how you do a sum of torques when there's rotational motion, actually. Not a statics problem, but a problem where there is rotational acceleration. And also making sure that you know how to deal with torques that are not tangent to the circle, or they're not perpendicular to the lever arm, where the radius, another name for that would be the lever arm. So this is the main idea of how to go about solving a sum of torque problem when there are torques at angles.